Okay, okay. I'm gonna start with a short background on the MRI mechanism. I'm pretty sure you are already aware of how it works. MRI machine usually has three main magnets, one main coil that produces the B0 field, and we know that the B0 field causes all protons to align with the B0 field. And on top of that, excuse me, do you hear the AC sound?
No,
Do you
no,
hear the noises?
no, no. It is good.
Is okay?
No, yeah,
Okay. And the B0 field causes all protons to align with the B0 field, and the protons start to process at a larger frequency, the larger frequency. And the point is that the proton is not completely aligned with the B0 field. There is a small angle with the axis of the proton and B0. So when it starts to rotate, there is a circular pattern on the tip, like that. The second coil we have is the gradient coil. The gradient coil is actually contributes to the B0 field, and it makes the B0 field inhomogeneous in different regions of the bore. So inside the bore, we will have different B0 fields in different regions, and it helps for a spatial encoding. And finally, we have the RF coil in the innermost part of the MRI machine. And RF coil produces a B1 field, and unlike the B0 field, it is not a static field. It is a time-varying field. It changes over time in a sinusoidal manner. And the B1 field is perpendicular to the B0 field. And when B0 and when B1 field is applied, two things happen. One, the protons start to fan out. By fan out, I mean that the Philip angle, the angle between the proton axis and the B0 field, start to increase. And the longer we apply B1 field, the greater become the Philip angle. And the second thing is that these protons become in phase. They process in the same direction with the same phase. Here, I have a better illustration. In the beginning, the tip is around here, almost in the same direction as the B1 field. Assume this is the B1 field, B0 field direction. When we apply the B1 field, the Philip angle start to increase. So it follows a spiral trajectory like this. And when we turn off the B1 field, it gradually gets back to the initial position. This is another illustration that shows what happens. And when we turn off the B1 field, because we have a great field along the transverse direction like Y or X, we can pick up this field by the received coils. Because when the proton is almost along the z direction, we cannot pick up any signals because the B1, B0 field is so strong that we can't get any signal from the protons aligning the B1, the B0 field. So we have to push it out away from the B0 field. And here you should pay attention that in this process, we still have a circular trajectory of the proton tip. So it follows a circular path. By increasing the flip angle, the radius of the circle increases as well. Uh, in modern MRI machines, usually the receive and transmit coils are separate. Here is an example of an RF coil for brain imaging. The outer cylinder contains the transmit coil, and this helmet contains the receive coils, and it can slide into the transmit cylinder actually. And here is an schematic view of how receive and transmit coils work in the MRI machine. This is the controller or the computer or actually the MRI machine. It sends a digital signal. It is converted to an analog signal using the DAC. Then the output goes to the RF pulse generator and amplifier. So the appropriate pulse is generated and then amplified and will be sent to the RF transmit coil to be generated. And here we have a transmit switch and receive switch. Why? Because we have to be able to control transmit and receive coils because these two do not work at the same time. When we transmit, when we are in the transmit mode, the receive coil is off. When we are in the receive mode, the transmit coil is off. So we have to be able to control each of these coils separately. And on the receive side, when the signal is picked up by the receive coil, the signal is pretty weak, so it has to be amplified and then mixed with the signal, get digital, and then send it back to the computer for post-processing. Okay. Remember that uh, this circular pattern of the proton when B1 field is applied. The point is that in order to increase the flip angle, we have to apply a B1 field with the same frequency as the Larmor frequency and the same direction. So we have to apply a circularly polarized magnetic field as B1 field so we can control and actually increase the flip angle and generate a field to pick up. But the question is that how can we generate this circularly polarized magnetic field? There are different approaches. The simplest way is to have two separate loops because when you apply a current into a loop, it generates a linearly polarized magnetic field. If we use two circularly polarized loops and apply currents with 90-degree phase shift to them, we will get these two. Actually, the blue line is the is due to the actually red. The blue arrow is due to the red circle or coil, and the green one is due to the blue coil. But since they are not in phase, they have 90-degree difference in phase, uh, their summation follows a circular pattern. So by combining two linear uh, magnetic field, we can create a circularly polarized magnetic field. There are different transmit coils that are used in practice. One of them, actually one of the simplest them, is the bird cage coil. Remember that here we use two loops with 90-degree difference, but we can use multiple loops with a different phase difference. So the idea here for the bird cage, it has two rings, one on the top, one on the bottom, and multiple legs connecting these two rings together. And there are capacitors between these legs. So what is the role of these capacitors? These capacitors produce phase shift because, for example, if we apply the transmit signal coming from the MRI machine to this point, then it goes here to the next one. This capacitor shifts the transmit signal by some degrees. So here we have a shifted transmit signal, and again and again. So in the simpler form here, we have only six legs. In order to have the right circularly polarized field, actually the transmit signal has to be shifted 60 degrees for each leg actually. So in this case, you see, the combination of these arrows creates a circularly polarized B1 field. And I should note that there are two main systems. One is single TX and the other is parallel TX. In the single TX, the MRI machine has only one output for the transmit signal, just like the bird cage. So you apply that signal to one point of the coil and you have to do the phase shift by some components like capacitors to get the right signal for the other legs. But the other system is PTX or parallel TX, parallel transmit. In this case, we have actually multiple outputs coming from the MRI machine. And it allows us to have a more uniform B1 field. For example, the system we have here, Siemens Terra, it has 8 outputs. So we are able to get 8 different transmit signals from the MRI machine and derive 6 different elements on the transmit coil independently. But the problem is that PTX, the design and verification of the PTX coil is much more complicated than the single transmit. The other common transmit coil is actually the dipole array. Just like here, dipole is a straight wire like this. In the middle, the input signal is injected into middle and it has two lengths to the up and bottom. And here there are 8 dipoles around the subject, generating a B1 field, a circularly polarized B1 field around the head of the subject. The good thing is that dipole can have better efficiency in deep tissues and it can lower the SAR. So it will be easier to follow the guidelines for the SAR using dipoles. And dipoles are actually a state of the art for transmit coil design, in particular for 70 or even higher MRI machines. The other notable transmit coil is the loop array. In the loop array, uh, loop, uh, loop elements are used here instead of dipole elements. So we will have loops everywhere around the subject. And actually, some people use a combination of dipoles and loops in the transmit coil as well. One important point that we have to take into account during the RF coils, during the transmit coil design, is to do the SAR calculation, because the transmit coil generates a time varying B1 field. It is not static unlike the B0 field. So that time varying magnetic field also generates electric field as well based on the Maxwell's equations. And this electric field can be absorbed by the tissues and increase the temperature of the body. And it can be dangerous, in particular for sensitive tissues like eyes and brains. And there are some guidelines that we have to follow for safety. We have to make sure that the SAR is less than 4 everywhere. And it becomes more important and actually more challenging in high field MRI, because the SAR is actually proportional to the to the to B0 squared actually. So when you go from 7 Tesla MRI machine to 7 Tesla MRI machine, the SAR is actually more than increased by more than 4 times, around 5 times. So it becomes much more challenging. It requires a lot of simulations and modifications to get the SAR, to bring the SAR lower than the standard value. And one of the approaches that people use to reduce the SAR is to reduce the duty cycle and also power of the transmit signal, but at a cost. It make the scan time longer actually. Now we start talking about the receive RF coils. Unlike the transmit coils, in the receive RF coils, the loops are actually by far most common elements used in the literature and even in industrial, in commercial coils actually. Here is a fabricated loop, and here is the draw of a coil, of a loop actually. The coil is made of a wire, a copper wire, in which several capacitors are inserted in between. So capacitors and the inductance of the loop creates an LC circuit or LC resonator, and the resonance frequency of that LC resonator is equal to the frequency of the coil actually. And we have to make it equal to the Larmor frequency of the scanner. For example, for 70 is like 297.2 megahertz. And depending on the size of the loop, we insert different number of capacitors, because we try to keep the length of the wires shorter than a certain value, certain length, because if these wires in between capacitors are too long, the current induced in this simple wire itself can generate a current that can generate some unwanted currents that makes everything much more challenging. So depending, for example, here, when we have a relatively small loops, the diameter of this loop is around 8 centimeter, we usually insert 5 capacitors. Once we build one loop, in order to find the resonance frequency of the loop, actually, we use the network analyzer. I don't know if you are familiar with the network analyzer or no, but I'm gonna introduce the network analyzer quickly. It is an instrument to measure and analyze the behavior of electrical networks, and these parameters actually describe how signal propagates through a network. For example, here we have a two-port network. S11 shows the reflected voltage from the first port. How? Imagine that we inject a voltage to this port, input voltage. It is shown as V plus because it is going inside, V plus. And because of the mismatch, a portion of this voltage reflects back. So this reflected voltage is denoted by V minus. The ratio of V reflected voltage over incident voltage is known as S11. It shows actually what percentage of the voltage or signal go through the device. And in case of two-port network, we can also define S21 or S12. S21 is defined in the same manner, is the ratio of the reflected voltage from the second port, the other side, or the voltage that comes out from the second port to the network analyzer over the injected voltage into the first port of the network. And here, in order to do the measurement, we use this dual pickup loop. It has two loops with an overlap. One loop is connected to one port of the network analyzer, and the other loop is connected to the other port. And how it works, imagine we want to measure S21. So the network analyzer sends a signal to port 1. So the signal goes into one of the loops connected to port 1, and it generates a magnetic field. The magnetic field due to the first loop or port 1 induces a current in the second loop, oops, in the second loop, and the current goes back to the network analyzer. And the network analyzer computes this ratio over a wide frequency band. But here, because of this overlap, a small current is induced into the other loop. So there is almost no coupling between these two loops. Once we put the loop, actually the coil, on the dual pickup loop, you see, at a certain frequency, we have a peak. Why? Because at the frequency corresponding to the resonance frequency of the loop, a higher magnetic field or a higher current is induced to the second loop, and we got a peak. And the value of this peak, actually this peak happens at around 300 megahertz, which is close to the uh, Larmor frequency at 70. And we always use a variable capacitor so we can adjust the resonance frequency exactly to the Larmor frequency. Because during the building the coil, we have to calibrate everything multiple times. It's not, we don't build it and just don't touch it. No, we have to calibrate it every time again and again and again. So we have to have some degrees of freedom. But once we calibrate the coil, we have to get the signal out of the coil and connect it to the MRI machine. So we have to connect a cable. There are different ways and different circuits to do that, but this is one of the most common circuits which is used to do this. So this is our coil. We have 5 capacitors here, and across this capacitor, we get 2 lines, and it is connected to the coaxial cable, and the coaxial cable carries the signal to the network analyzer or the MRI machine. And here we have a match variable capacitor as well. Why? Because the impedance of the coil here is not necessarily the same as the impedance of the coaxial cable. So this capacitor matches the impedance of the coil to the impedance of the coaxial cable. And in addition to these capacitors, we have some other components inside a loop. First, we have a fuse. Why? Because if some, if for any reasons a huge current is a huge magnetic field passes through this loop, a huge current will be induced inside the loop. And this fuses breaks the circuit, breaks the loop if the current goes higher than a certain value, because this is the receive loop. The receive loop just want to pick up a tiny signal from the brain or the other tissues. So the induced current should be a very, very small current, not a huge one. So here there is another safety step actually. We have a capacitor in parallel with 2 cross diodes. So when the current induced inside the loop is a small, everything works just fine, no problem. This diode don't do anything. But if the current goes higher than a certain limit, the voltage drops across the capacitor increases. And when it goes higher than the forward bias voltage of the diodes, no matter what is the polarity, one of the diodes will turn on and make uh, this part short circuit. Actually, it bypasses the capacitor. So then when you have when you no longer have this capacitor, the total capacitance of the loop changes, and so the frequency, resonant frequency of the loop, so you can't get any signal anymore. And finally, here we have another safety by adding an inductor and a pin diode in parallel with this capacitor. How it works, we connect 2 DC bias lines to the 2 sides of the pin diode. By applying a DC voltage across the pin diode, we can turn it on or off. When we turn it on, it becomes short circuit. This L goes in parallel with this C, and the L should be selected in a way that L and C in parallel uh, have resonance frequency at the Larmor frequency. So at the Larmor frequency, these two resonance and show a really high impedance. it's like an open circuit because a parallel LC circuit had a very high impedance at the resonance frequency. So when we turn this diode on, we will have an open circuit here, a very high resistance here. So no current will be induced inside the loop. Here, these are three safety measures that we use inside a loop. But depending on the application, to be honest, we do not use all of them in every coil. Uh, for pediatric coils for children, we use more safety measures because the kids are more sensitive and they may not notice that some problem is happening. But for adult coils, we usually do not put the fuse. We usually have just the this part, which is called active detuning. So here, from the coil, actually we have two types of output. One is the coaxial cable that carries the signal coming from the loop, and two DC bias lines that can be used to control the pin diode. And these are the actually connectors for the Siemens Terra machine, 7 Tesla. The left one is for the receiver, and the right one is for the transmit. On the receive side, you see there is a large BNC connector in the middle. It's for the transmit. It can be used for the transmit. There are 8 small BNC connectors. These are for receive loops. So the coaxial cable coming from each receive loops is connected to one of these small BNC connectors. And here on the top we have some single pins. These pins can be used to control the pin diode. After and the left and the right one is for the transmit coil. In this machine we have it can support up to 8 transmit coils, and this middle one are the DC lines. And once we build the coil, we have to write a code. So we have to write the code to tell the machine, okay, which coil is connected to which channel and what are the bias lines, when turn this on, when turn this off. So we have to write a coil file to control our coil. As I told you before, since the signal is too weak, we have to amplify the signal using a preamp, just like here. The signal goes to the preamp, and ideally, we may want to connect the preamp directly to the coil output without a coaxial cable, but most often it's not possible. Why? For example, if we have coils for small animals, we have no space to put the preamp next to the coil, or for adult coils, actually, for example, brain coils, the we would like to keep the preamps far away from the transmit coil because the field generated by the transmit coil is so strong that can interfere with the preamp or even damage the preamp. So we put a wire in between to put the preamps far from the coil actually. But the problem is that we know that a coaxial cable is a kind of transmission line, And when you have a piece of coaxial cable, for example, of length L, and here the impedance from this point is Z load, the impedance we can see from this side is no longer Z load. It's something like this. Why? Because the wave that propagates in this side inside this cable experiences some delays because it takes time, and this delays causes some phase shift. So the signal that comes here has a different phase compared to signal here. And we have to fix it. We have to have the same phase here as here. So we can do two things. One thing is to use the appropriate cable length. So we have the same phase. We experience no phase shift inside the cable, but it's not always possible because sometimes that cable length might be longer or shorter than what we need. So the other approach is to add a phase shifter circuit here between the coaxial cable and the preamp. So it can compensate the phase shift of the signal. So we can see, so we can the same impedance from the preamp point of view. Another issue that we have with the coaxial cables is that we actually have two types of transmission lines. We have balanced and unbalanced transmission lines. In the balanced case, just like a pair of twisted wire, we have similar wires, so they have similar impedance. There is no problem. When you apply a voltage, the same current go through the wires, but in different direction, just like here. But in case of the, let me just, but in case of coaxial cable, it's no longer the case because coaxial cable has an inner core like this, and outer shield, it has a thickness. So these two do not have the same impedance. So what happens, in addition to these two currents, another current known as the common mode current actually flows over the outer side of the shield. And this current is most often unwanted because it can radiate into the room or cause interference with the neighboring loops or coils. So we would like to get rid of it. And there are three main solutions to do that. One solution is to use this. One solution is to use ferrites like this one. You, all of you have seen this ferrite uh, around the like USB cables or the other cables. It actually do the same thing. But the problem is that these ferrites are ferromagnetic and it's a magnetic material, so we cannot use it inside the magnet room. The other solution is to use tank circuits. The tank circuit, something like this, it can do the job for us. But a more popular choice is to use the cable traps. We have different types of the cable traps here. This one is actually the coaxial cable with a capacitor soldered to the outer shield. Here we have the same thing, but as a different module. So it is composed of multiple turns of the coaxial cable with a capacitor soldered between the outer shield of the coaxial cable here and here. So we can solder one side of the coaxial cable to here and the other side of the coaxial cable to here. So the signal passing through this cable trap, uh, the common mode will be cancelled out. Once we build the cable trap, we have to adjust it because cable trap is a kind of, again, filter is a kind of LC circuit. It has a resonance frequency, and that resonance frequency has to be the same as the Larmor frequency. So again, we use the dual pickup loop to measure the resonance frequency of the cable trap and adjust it to Larmor frequency. This is another type of the cable traps. It is made of two layers of copper plate. In between these two copper plates, some capacitors are installed. So again, it makes an L and C, an LC circuit. By adjusting these variable capacitors, we can adjust the resonance frequency of this cable trap to the Larmor frequency. The good thing is that to use this type of cable trap, we don't need to cut the wire. It can easily go around the wire, but it's much bigger than this type of cable traps. So far, we have discussed just one single coil, but the problem is that in mm, in many MRI, in many coils, actually, uh, more than one coil is used because there are some advantages to use multiple coils actually. One is that in case of using an array of coils, we have a better SNR, in particular that when we have some conformal arrays, just like a head helmet that goes around the head. The other advantage is that it shortens the scan time through the parallel imaging because we have different arrays, different elements, and each of these elements pick up the signal just from a certain portion of the subject. So we have some knowledge about the location and the area that is covered by each loop. And it helps us to do the reconstruction much faster. And here is a photo or a photo of an array. Uh, there are two strategies. One, we can group multiple coils together inside an array. For example, here we can group every three coils together. So to have a four element array, because each of these three is considered one coil actually. The other is to have separate arrays, separate coils. Each of these coils can act as a separate coil, but the number of coils is limited by the machine you have because the number of receive coils is limited. For example, here the machine we currently have can support only up to 64 receive coils. And I've seen some machines that can support up to 128, but it's usually not more than that. So, and here I have another, sorry. Hmm, hmm. Another issue is that when we are working with an array, all of these elements are working at the same time. All of them are receiving signals. They are connected to a circuit. So they actually communicate to each other. There's a crosstalk between these two elements or a coupling between these elements, adjacent elements. So we have to find a way to reduce this coupling. One way is to use geometric coupling. What does it mean? When two adjacent loops have a certain amount of overlap, it can be shown that these two loops are actually decoupled. There's a very small coupling between these two loops. If they get far away each other, or if they get closer to each other, the coupling increases. So there is a certain point that at which we have the minimum coupling. Here, here's a photo of one of the coils that we are building right now in the lab. You see here, it has 32 loops in the final design. It has 32 loops, and here are the loops, and you see every loop is overlapped with the adjacent loop to reduce the coupling. But the problem is that uh, when you have many loops inside the helmet, in the beginning it's easy to do the coupling, but after installing a certain amount of the loops, it gets more and more difficult to do the geometric decoupling because you no longer have flexibility. All of the coils are already installed. So we have to have some other decoupling strategies. One of the most common decoupling strategies that is used is preamplifier decoupling. What does it mean? Preamplifier, if we use the right length of the coaxial cable, and there are some capacitors here, it's not shown here, but with the right length of the capacitor, of the cable and the capacitors here, we can see a very huge impedance from this side because the impedance is transformed over the length of the cable. In that case, the current induced inside the loop do not pass through actually because it's a huge impedance, so you can't see anything at the output. Here is a diagram of a coil, actually of a loop in with and without preamp decoupling. In here, there is no decoupling, you see. There is a peak, we have a good output, but when we apply the preamp decoupling, we see a drop in the signal, so we can't get anything out of it. This geometry decoupling together with the preamp decoupling helps us to make the coils decoupled from each other. And it is necessary to have a good performance. If they are not decoupled, we will not get a good result. So far, I have reviewed the principles of RF coils quickly, and I just want to go through the B0 shimming because the project that I'm currently working on is for B0 shimming. We don't have that much time, so I'm gonna. Okay. Let me just ask you if you have any questions so far before going to B0 shimming. Is there any questions? You can consider as loop antennas. When we apply a current to one of them, a current goes inside this loop and a magnetic field is generated inside the loop, right? And when there is an overlap, some portion of this magnetic field goes through the adjacent loop and induce a current, another current inside this loop. But since there's an overlap, the current going through, because not the magnetic field going through this overlapped part is in opposite direction than the magnetic field going inside the other part, right? Because the magnetic field from the left loop, for example, is coming out from the screen. So for the overlapped comes out, for the non-overlapped part goes inside the screen. So for two parts of the loop, we have currents induced in two different directions, and these two cancels out each other. So we don't get any current out of this second loop. So there's no decoupling because we can say there's no decoupling because when we apply something to this one, we can't get anything on the second one. It, does it help? Does it help? Hello?
Yeah, yeah. I think we can continue and we can ask maybe questions later. That's better. Yeah. Let's-
Okay. But I'm not, because the builder shimming is a long topic, but okay, let me just cover it in a few minutes. Uh, we know that in order to have a good quality image, we have to have a homogeneous B0 field, but in practice, it's not possible because there are hardware limitations and there are magnetization because of the tissues, and it this becomes worse and worse in high field MRIs because in homogeneity grows linearly with the Bezier field. So we have to have some measures to solve the Bezier field in homogeneity inside the subject. For example, here we have images from 3T MRI and 70 MRI. You see the B0 shift in the 3T is much lower than the 70. In particular around the nasal cavity, around the ear canal, we get a much worse shift. And when we have such a huge shift, we can't get anything, we can't see anything. So we have to find some way to solve this problem. There are some remedies. For example, there are some algorithms to do the corrections. But the other approach is to eliminate B0 field in homogeneity itself. How? There are two different ways. One way is passive shimming. Passive shimming is just placing some magnetic materials inside the bore to make B0 field more homogeneous. The other way is active shimming. Active shimming falls into two categories, spherical harmonics, which is already integrated into most of the scanners, and the other is to have some local shim arrays. So we can place some DC coils that generate B0 field around the subject to counteract with the B0 inhomogeneity inside the subject, inside, for example, the brain. For example, here this is an example. These loops installed on the top and bottom of the head, DC current will be injected into these loops, and the B0 field generated by these loops can be controlled to cancel out the B0 inhomogeneity inside the subject. The other way is to have both receive coils and the B0 shim coils inside the same coil, just like this. In this diagram, the gray lines indicate the standard receive coil. You see here's the coil with the capacitors and passive active tuning, coaxial cable, and the preamp. And we add some components to add beat-through shimming capability. So we have some inductors installed here, here, and here, and some capacitors here. So what happens when we apply a DC voltage to here? The DC voltage goes through the inductor, and from the point of view of a capacitor, uh, it the DC voltage cannot pass through the capacitor, so it goes here, then go through the inductor. It does not go inside the circuit because these capacitors block the DC signal, and again and again, and it comes back here. So the red path, the red path shows the path in which the DC current go through. So here, and the gray path shows the way that the AC signal that the signal picked up from the brain go through, which is the standard signal. So we can have both DC and AC and DC V0 shimming functionality in the same coil. And here's an example of 8-channel coil we have built. These are the chokes we have installed across each capacitor. And here I have some photos of the S parameters measurements with and without chokes. So you see here we have no chokes. This is the standard coil. And here all of the chokes are installed. So uh, there is no significant difference in the S parameters. So the performance of the coil is not degraded by installing the chokes. And the same thing happened in case of the detuned coil. But the problem is that it requires a complicated setup to control the current, to calculate the current, and it's a big project itself. Okay, I think it's enough. I don't want to take your time more than this. And if you have any questions, please feel free to ask.